Hey, good morning. How's everyone today? Is my voice coming through? Very good. Thank you. Okay, so we will begin today's class. We have two topics to be covered today. We will cover DC analysis and we will cover MOSFET as a switch and an amplifier. So please I need your full attention, at least for the first one. Second one, I leave it back to you. Right, so welcome and let's begin. What are the steps for DC analysis that you need? This is what we had learned in last class, and we will quickly cover briefly once again. First, you need to assume. What? Assume an operating mode. Pick the nearest one with an intelligent guess so that your analysis becomes faster. Second, enforce the conditions, the equality conditions in that mode. Then analyze the circuit. After you analyze, check for the inequality conditions, the VGS minus VT conditions, VDS conditions, okay? And then finally modify your original assumption and repeat all the steps if it is not consistent. If it is consistent, you are done and you can exit. So let us do that with an example, because that will be easier to understand. So what is the example we will teach today? First, we will do a simple NMOS device. And with that NMOS device, you have a resistance connected at the drain. You have a resistance connected at the source. The gate is connected to ground. Now, how do we proceed with the analysis? Let me ask some of the regular attendees who have not answered till date. Hemashri? How do we proceed next? Okay, I'll ask a simple question. What is the mode that we begin with? Okay. She said yes, sir, and went away. Okay. Lasya Priya?
Yes, sir. Am I audible?
I can't hear you.
Yes, sir.
I can't hear you. Speak up.
Hello.
Hello, yes. Are you people intentionally doing this, or are you really cannot speak up?
Yes, sir. Am I audible?
You are not, you are very feeble. Can you speak up is what I said. Speak up meaning speak loudly.
Sir, maybe there is an issue with my speaker. I'm not sure. I'll check it.
Okay, how do we proceed? Anybody else?
Assume operating mode.
Come again?
We have to assume operating mode.
Yes, what is the operating mode that you would like to suggest? Okay. Okay, what do we know from the circuits that you have here? What do we know about this one? What is VGS?
Sir, am I audible now?
Yes, you are audible.
Yes, sir.
Yeah, what is VGS? Gate to source value.
5 volts, sir.
5 volt. This is your gate
Yes,
This is
gate
source.
VG is 0 and VS is connected to -5 volt.
Is Vs connected to -5? There is a resistor there, right?
Yes, sir. Yes, sir. Sorry.
So what is VGS? Okay. Looks like people are really not paying any attention to class. No interest in giving answer. I'm saying this on record. Okay, what do you start with? You start with first is you can do a Kirchhoff voltage law. Where do you do Kirchhoff voltage law? Start here. So what do you start with? Gate is connected to ground, so it is 0. Then this is VGS and it is in this direction. So it is minus VGS. Then further, the current is going to further get reduced. What is the current drop through the resistor? Current drop to the resistor is 1 kilo ohm times ID. And that final voltage is -5 volt. Okay. Sai Chandana, what's the next step? Rearranging, we get ID is equal to 5. 5 will come this side and say, so it is 5 minus VGS. ID in 1K has gone this side, so you will get 1K. This is equation 1. This is another. We get one more loop here. So this is the other loop. KVL at drain source loop. What do you get? Start from here, the top 5 minus 1K times ID minus VDS minus 1K times ID is equal to -5. Rearranging. What do you get? Okay. VDS goes that side. So
10 minus
VDS.
VD is by 2K, sir.
Sorry?
ID is equal to 10 minus VDS by 2K.
ID is equal to, sorry. ID is equal to 10 minus VDS divided by 2K. Okay. So this is equation 2. Now, what is ID? Half mu n Cox W by L VGS minus VT the whole square. This is ID. Now we know this value is defined as K. So ID is equal to K times VGS minus VT the whole square. We have VT value is 2. We have VGS is an unknown, ID is unknown. So how do we proceed further? How do we proceed further? Very simple. Substitute this equation here or equate these two. Either one is possible. So what happens when you equate 1 and 2? Easiest thing to do is eliminate one common, keep only one common factor. So here there is VDS, here there is VGS. This equation has VGS. So bring VGS equation here. 5 minus VGS by 1K. So that is ID. So now if you equate this, what happens? K times VGS minus VT is 2. 5 whole square is equal to 5 minus VGS divided by 1000. This I'm writing so that we don't confuse between this K and this K. Or we will replace this K here itself. .4 milliampere per volt square. Okay. Now if you equate, milliampere will go away with kilo. So what is left over? 0.4 times VGS minus 2 the whole square is equal to 5 minus VGS. What does this become? This becomes a quadratic equation. Correct? So 0.4 VGS square minus 4 VGS plus 4 equal to 5 minus VGS. So when you rearrange, what happens? VGS square minus 4 VGS plus 4 equal to 5 minus VGS by 0.4. So 5 divided by 0.4 is how much? Simple. 5 divided by 0.4 minus VGS by 0.4. 4 by 10 or 5 by 2. Right? This is 4 by 10 or 2 by 5. 5 when it goes to the numerator becomes 5 by 2. This becomes 2.5. Similarly, 5 into 2.5. So now when you rearrange here, VGS square minus 4 VGS minus 2.5 VGS is minus 1.5 VGS plus 4 plus how much is this? 12.5. So it is minus 8.5 equal to 0. So when you find the solution of this equation, what do you get? I've already calculated that. So VGS equal to, you get 3.76 volt, or VGS is equal to minus 2.26 volt. Is this consistent? Yes. Because if both are negative, then one term has to be positive. So because one is positive and one is negative, you will have the product with a negative sign. And there is one which is greater than the other. So you take a difference of these two, you get 1.5. So that is how you quickly verify. So you have VGS is equal to 3.76 volt or minus 2.26 volt. No. What is the correct one to use? We will see. Now let us see. VT is equal to 2 volt. VGS equal to 3.76 volt. So what does that condition give? VGS greater than VT. What does this mean? This is in saturation mode. No, that means it is, the device is turned on. We don't know whether it is in saturation mode. Okay. So device is on. Okay. Now, if device is on and if we can call it, it is in saturation mode with our initial assumption, then our ID current becomes ID is equal to K times VGS minus VT the whole square. So we have VGS, we have VT, and we also know that K is equal to 0.4 milliampere volt square. So substitute 0.4 milli times 3.76 minus 2 whole square. Can somebody calculate and tell me what this answer is? What is this answer?
$38.33.
38.33.
1.23 milliampere, sir.
1.23.
1.23, sir.
1.23 milliampere.
Okay, 1.23. Who is that person? Okay, 38. Please tell me. What mistake did you do? Now they will go silently. Okay, so this is the current equation that you have got. Right, it is 1.23 milliampere. Now we found out what is VGS, we found out VT, we found out ID. Next, we need to find out another inequality is VDS. Now, what equation can we use for VDS? We can use this equation. ID is equal to 10 minus VDS by 2K. Now, find out what is VDS. So VDS is 10 minus 2K times ID. Quickly tell me this value. What's the answer? VDS is 7.54 volt. Now with this 7.54 volt, let us see. We said assume saturation, right? So what is the conditions for saturation? VGS is greater than VT and VDS is greater than VGS minus VT. Now let us write the answers on the other side. How much is VGS? 3.76. VT 2.0. Okay, this is fine. VDS is 7.54. VGS minus VT here 1.76. If you see what happens here, this condition is satisfied. This condition is also satisfied. So with these conditions, our solution is correct. Right? So device is in saturation. Right? Understood? Yes or no? So what are the design variables in this case? This is what you have to understand. This is called the design variable space. Design variable space. First thing is VGS, voltages, VGS, VDS, VT. Then comes your current and transconductance. We did not calculate transconductance. Let us calculate that here. Okay, then what is GM? What is the equation for GM? GM equal to? Yes, tell me. What is GM equal to?
UNCOX into W by L into VGS minus VT, sir.
Mu n Cox W by L into VGS minus VT. Can you tell me in terms of ID and any other variable?
2ID by VGS minus VT, sir.
2ID by VGS minus VT. Very good. We will use this one because it is easier. Now, what is 2ID? How much is ID?
1.23 milliamps.
2 times 1.23 milli. Divided by how much is VGS?
3.76 volts.
3.76. VT is
2 volts.
2 volts. So it is 1.76.
76.
So can somebody give me what is the answer here? How much is GM? Got it? Open your calculator, type this number. How long does it take?
So 1.39.
1 point?
39.
What are the units for GM? You've got ID, you've got I and V. So what are the units for this one? Is the value 1.39 always? People have to learn or they have forgotten. Huh? Milliampere per volt. This is ampere here, volt here, units. And this milli is carried forward. So this is your GM. Okay. Remember, in the exam, when I ask, obtain the design variable space, all these 5 needs to come. Even if one is not there, marks will be deducted as pro rata. Next, we will do another question, just so that you people are aware. Okay. Now, who can take us forward with this one? How many are there today? 12. So half the class only. Sai Chandana. Now your turn. Can you please come on video? Let me see at least how you think. What is your face expression when you think? Yes. Start. So where do you begin this problem? There is a PMOS
VGS.
transistor. Okay.
Yes, sir.
You start with VGS. Okay. Do you know what VGS value is? Thing is, you need to find VG. So that is what you have to find. So let's go to that to the end. So what all do you know here? That would be the nice way to start.
VS 5 volts.
Vs is 5 volt. Okay. Correct. Then
VD 4 volts.
Vd 4 volts. Okay. Then so from these two, I will write VSD is equal to 1 volt. Okay. Then VSD equal to 1 volt equal to minus VDS. Negative sign, no? So VDS is minus
Minus.
1, VSD is 1 volt. Okay, what next?
VDS is -1.
Okay. Can you find out current ID?
Not black color, pink color. You
Okay, I'll use pink color.
one is pen.
Yeah, what is ID?
Mama,
Okay, I think I'll bring on one more person.
not like this.
Lasya Priya, turn on your video. Meanwhile, Sai Chandana, you have to find an answer and tell me.
Yes, sir.
Is Lasya Priya in the class or she has just turned on the class and gone away somewhere?
Mama, not the pink. Draw.
Yes.
You like anybody.
What is ID?
That is not working.
I'll calculate it, sir.
Okay.
Sorry?
I'll do it, sir. 1 minute, sir. I'm doing it.
Only like this.
So till now you are busy somewhere else.
No, sir. No, sir. I'm just I'm thinking of doing the KVL and finding out.
Sure,
VDS.
sure. Tell me which KVL you'll do. We'll do it here itself.
Sir, we can do from source to drain.
Source to drain KVL is already done, right? 5 volt.
Mm.
VDS we have found. Done. What else is pending?
But I cannot. get
Okay.
out of it.
We will do KVL.
Why, Ma? Like the pink.
KVL at
Red.
drain to source loop. Tell me, what is it?
Color. Pink color. Pink color.
How do you start?
Pink color. Pink color.
Mm.
Yes. That would look
Hmm.
color.
Go on.
It's not okay. Red,
Minus
red color. Color, Ma.
4 volt.
Color.
ID.
You know how to do one. Me.
Why don't you tell me what you're doing? We can do it here for the benefit of the class.
Sir, I think ID is 0.25 milliamps.
ID is how much?
ID is equal to
0.25 milliamp.
0.25 milliampere.
Okay, this is Lasya Priya. Okay, anybody else has a different answer? I want to know how you got this.
Mama. Mama.
So basically, I have applied KVL. So
Apply.
basically,
Go ahead. Start. Where did you start with? 5,
from
right?
source,
Okay.
yeah.
Source.
Ma.
5.0 volt minus
Ma.
VDS.
Minus
Like yellow.
Okay, now this is VSD. Then
These are you should not set.
minus
What the fuck?
VSD.
then
Then I had to do what?
So I took minus 4K into ID.
minus 4K into ID. Okay.
Take
Okay.
off this.
Then
Take off.
is equal to
Where's the lip of the Ma? Take off. Take off and he's taking off.
Minus
Not bigger.
1 minus 4K
Take off.
into ID
Take off, Ma.
equal to 0.
Take off. Take off.
4 is equal to 4K
Take
into
off, Ma.
ID.
This one bad color.
ID is equal to 1 milliamp.
Take off. Should not bet this bet.
How much is it?
Take
ID
out.
equal to 1 milliamp.
Take
sir.
out.
I think
1
I-
milliampere. This is correct. 1 milliampere is correct. That is what I was trying to see.
Yes, sir. I think I have done some mistake before.
You know what is the easiest way to do it? This is VD. Current to this resistor will be the same. So
Yes, sir.
VD is 4.
Yeah, so by Ohm's law, we can do
Exactly.
I is equal to V by R.
Come here.
So you guys unnecessarily complicate it.
It's not going.
Why do you complicate it? It is simple.
Yes, sir.
ID is equal to VD by 4K.
By 4K.
So it is 4 by
4
4K.
by
Is
4K, which is 1 milliampere.
milliampere.
Take off the.
Fine.
Bet is not long.
No, I want this one. Thank you. So what is, now you found ID. Now, what is the connection between ID and VGS? Because you need to find VG, right?
Yes, sir.
Okay. What is the connection between ID and VGS?
Oh no. Either.
ID and wages, like we can, since we were given VT, we can use formula, sir.
That is what I meant. What is the formula?
IDS is equal to 1 by 2 mu n COX into W by L into VGS minus VT whole square.
Okay. So that is the ID equation. So this is equal to K times. No, what is the assumption? The assumption is it is in saturation region. Huh?
Yes, sir.
Okay. Excuse me.
What is long? Eight one in this one.
So this is VGS. Sorry about that. So it is VGS minus VT.
Oh. Okay. What does it make? So everybody.
VGS minus VT,
It starts.
the whole square. So we know K, you know VT, you know ID.
You don't like this.
Find VGS.
VGS
What is VGS?
Ba.
plus 2 whole square.
Ba.
ID is 1 milli. So VGS plus 2 whole
So
square
VGS is equal to
equal to 1 by 0.2,
ID divided by
which
K
is
whole root
1, which is equal
plus
to
VT.
root 5 minus 2
So how much is VT? VT is
minus 2.
minus 2. What's the answer?
But it's root 5 minus 2. I'll simplify it more.
Y minus 2? Root 5 minus 2, correct. Okay.
Root 5 minus 2.
P is minus 2 plus ID is how much? 1 milliampere. And
0.
how much is that?
0.23 volts. VGS is equal to
This one color, Ma.
How much is it?
0.23
0.23.
volts.
This is 0.2 milli.
VGS, VG
Root 5 is 2.235. Okay. So
yes, sir, 2.236.
235.
So minus 2 will get 0.23.
Right. Now, what is this? Is one KVL you applied, which was not used. What is the other KVL you can use to solve this? Use KVL here. So what will be the-
VG. Since we need VG, like VGS is equal to VG minus VS, we can do. Since we have VS, VG is equal to
Start from here itself. VG. Now, important thing is, what is S here? This is VGS, right? This is
yes,
drain.
sir.
So what
Yes,
is
sir.
VGS is equal to VG minus
Minus
VS.
5.
VG minus VS.
So it will be
Since we got VGS is equal to 0.23 volts and we have VS, we can get VG from there.
correct. So this is equal to 0.235.
It will be
How much is VG?
5.235 volts.
Come again, 5 point?
235 volts.
VGS minus VG minus VS, right? Okay.
Yes, sir.
Hmm.
So since so we'll get VG is equal to 5.235 volts.
You are going negative, right? So this will actually be minus 5, right? Source, if you do VGS, VSG is okay. So you are saying VGS is equal to VG is equal to 5.235. Correct?
Yes, sir.
Okay. Now, now have you got all the design space values? What are the design space values?
VT, VGS,
Hmm.
and VDS.
Okay, then
IDG.
ID and GM we need to find out.
right. How much is GM?
GM is equal to 2 ID by VGS minus VT. So
okay.
2 into, since ID is 1 milliamp,
Hmm.
2 milliamp by VGS we got as 0.235. So
Hmm.
0.235 minus VT, which will be plus 2 volts.
Hmm.
So we'll get it as 2 by 2.235 milliamp per volt. 1 minute, sir, I'll calculate it.
Approximately
2
0.7,
by
0.8
2.235, 0.89 milliamperes per voltage. So
milliampere volt. Okay. Now check. Our initial assumption was it is in saturation.
saturation mode.
Okay. Now let us check if all the variables are in that way. What is the check that we do?
If VGS is greater than or equal to VT or not, and if VDS is greater than VGS minus VT or not.
Right. Now, can you check if that is correct?
Yes, sir. So VGS is 0.235 while VT is minus 2. So definitely VGS is greater than VT. And VDS, we got it as minus 1. So if since we got VGS as 0.235 and minus will become plus, right? So VGS minus VT will be
2.235.
2.235. The VGS greater than, VDS greater than VGS minus VT condition is not satisfying, sir.
Come again.
VDS greater than
Hmm.
VGS minus VT condition is not satisfying. Basically, VDS is less than VGS minus VT. So we can say that the MOSFET is in linear region because VGS is greater than VT, but VDS is less than VGS minus VT.
That is correct. Okay. Then, so I'm sorry, I couldn't pay attention. So VGS minus VT. So it is in linear region, is what you said.
Yes, sir.
Okay. What is VGS greater than VT?
Yes, so VGS is greater than VT, but VDS is less than VGS minus VT.
All right. So this is okay. So this says that this is in linear region. Now, let me tell you where we went wrong. Okay. All this calculation is wrong. What is VG value? Where did we go wrong? Remember, this is defined for an NMOS device, whereas you are working with a PMOS device. So how does the equality change?
Everything will be reverse of NMOS, sir.
Reverse of NMOS, correct? Now, let us begin from fresh. Okay. This is what I said, you have to pay attention in class. Blindly following is not correct. Okay, let us begin.
coming.
First of all, what is the equation for this one here? Since we have to find VG, let us define what are the values. What is VDS? VDS will be equal to minus VSD for PMOS, so ulta. VT will be minus VT for them.
Oh, right.
VGS will be minus
I love
VSG.
blue. All right, yellow.
Okay. Only thing that doesn't change is ID. Your ID is 4 divided by 4K, which is same,
1 milliampere.
1 milliampere.
Papa, I think I want.
Please write. Okay. So here we also know Vs is 5 volt. So these are the two things given right in the beginning. Another thing you have to understand is, does current flow here? Does current flow here?
Papa, I can write this.
Write this one.
ID is equal to 1 milliampere.
Always remember, there is no current flowing into the gate of a transistor. Ig is always 0. So this impact of 10K is nothing.
Not being
No current flow at all.
Yeah.
So what is
Papa,
VG then?
Papa.
What is this gate voltage here? It is this VG minus 10K. If you apply KVL there, VG minus 10K times IG is equal to this total voltage here. This is, so if this is 0, whatever you apply here will apply here also. So VG is present here itself. Clear? This voltage is seen at this point also. There is no drop across the resistor. Understood? This is the first thing. Next thing is find out what is VDS.
VDS
Current to
minus
source.
1 volt.
Right? So VD is VD minus VS. That comes out very simple to be, how much is VD?
4 volt.
VD.
VD is 4 volt.
4.
VS is 5 volt.
So how much is it?
Minus
Minus
1.
1.
Minus 1 volt. So now you found out where the error was. Everybody is saying 1 volt from that time. Because in the mind it has sat down that top is drain, bottom is source. So you said 5 minus 4, 5 minus 4. No. Drain is here. So it is 4 minus 5. Got it? Now, what is VGS? VG
Papa.
minus VS.
Papa. Papa.
So it is VG
Papa.
minus 5.
Papa.
Okay? Clear? You know where the mistake was done? Next, we will take next step. Now we know ID, right? What information can we gain from here? We need to find VGS. So, Sai Chandana, what is the equation that fits here?
VT equal to K into VGS minus VT whole square.
VGS minus VT the whole square. So in this equation, what is pending to find out? VGS.
VGS.
Let's find VGS. How much is that? K is given as 0.2 milliampere. So 0.2,
Papa. Papa.
0.2 milliampere VGS minus VT. How much is VT?
Minus
Minus 2. VT is minus 2. Whole square. So that will be 0.2 milli VGS plus 2 the whole square. Okay. So now this is equal to 1 milliampere. Milli cancels. 0.2 when it goes below, this becomes 5. So 5 is equal to VGS
VGS plus 2 whole square.
whole square.
VGS will be 0.236 volts.
Hmm?
VGS is equal to 0.236 volts.
VGS is equal to 0.236
236 volts.
volt. Now, since it's a square root you're finding out, you should be one more value should be there. What is that? What is it? VGS plus 2 is equal to square root of 5, and this is plus and
Plus
minus.
or minus.
One value you have told. What is the other value?
Minus 2.23.
This is
Minus
plus minus
4.236.
How much is it? Minus
Minus 4.236 volts is other one.
4.236 volts. Okay. Now let us see the previous one. What did our VGS come out to be? See the difference here. You saw the mistake where it was. Mistake was here. I said VSD is 1 volt and VDS is minus 1. This was a hint I gave. But still people continued everywhere VDS is 1 volt itself. Okay. Now let us proceed. Now we have found VGS. We have found VDS. Right? Now VGS is this value. Now we have two equations now. Right? Which is the equation that we can use? VGS should be less than VT for PMOS device.
Yes, sir.
Okay. Now find out which equation satisfies this one. What value satisfies this one?
VGS is equal to minus 4.236 volts will satisfy the conditions.
Minus 4.4236
236.
less than minus 2. Okay. So this is device is on. If I use the other value, device is off.
Yes, sir.
So to use 0.236, this is device is off. Okay, this is wrong. Okay, this is one assumption. Right? What is next? VGS minus VT we have found out.
To check if VDS or not. VDS minus 1. VGS minus 4.
Okay, before you go there, find out what is VG value. VGS is equal to
VS is equal
VG minus VS. So this is minus 4.436. Minus VG minus VS. How much is VS? 5. So what is VG value?
0.764.
0.764.
764.
So this is the answer to the problem. It is very, very easy to get lost in analog circuit design if you don't follow the basics correctly. Right? Now, in this case, this is assuming saturation, right? We started off with a saturation equation. Only one equation is satisfied. Now let us go to VD. This is still not correct. This is correct only when it is saturated. So what is VDS value then?
VDS we got as minus 1 volt.
How much is it? How much is VDS?
minus 1 volt.
Minus
sir.
1 volt, right? Now you tell me, what is VDS relationship with VGS minus VT?
VGS minus 4.236 while VT is minus 2. So minus 2.236. VDS is greater than VGS minus VT.
So this is minus
VGS
2.23.
2.236 while VDS is minus 1 volt.
VDS is minus or
Minus
plus?
1 volt and VGS minus VT is minus 2.236.
Minus 2.3. This is minus 1. So this is greater. What does this assumption mean?
It's in linear mode.
Linear mode.
Saturation.
Saturation mode. Remember, this is PMOS.
Yes, sir. So for
Cutoff,
PMOS, everything is in reverse
Hmm.
of NMOS. So,
So if
when we
VDS is greater
consider
than VGS minus VT, it will be somebody gave the answer. I'm only confirming.
Cutoff, sir.
in
Cutoff? No,
linear
because it
mode.
is on, right? VGS minus VT. So device is on. It cannot be cut off. So it is linear or triode region. Remember, for PMOS, this equality is ulta.
Yes, sir.
If VDS is less than VGS minus VT, then PMOS is in saturation. Okay? Clear? Not clear?
Papa. P. Yes.
Clear? Not clear?
Clear, sir.
Clear.
Papa.
So how do we proceed now? That means this equation that we found is incorrect. Our assumption is wrong now. Assumption is incorrect. Right? We start off with a saturation. mode,
Saturation
right?
mode.
That assumption is incorrect. So the correct assumption should be
Linear.
linear mode. So what is the equation for linear mode? ID current for linear mode. We learned it last class. Quickly pull up. Okay. Let me call up somebody else. Dhanashri, please turn on your video and we'll continue from there. Dhanashri and Kajal. Now these two will help in answering from now. What is the ID current in linear mode? Of mu n Cox W by L, I'll replace it by K. K times Chandana Lasap, you are okay to answer. If you have got the answer, go ahead. Huh. K times
K times VGS minus VT into VDS.
into VDS. Then
K times of 2 into VGS minus VT into VDS minus VD whole square.
VD whole square. Okay. Now fill up the values here. What do we know?
K is
ID is
0.2.
I is 1 milliampere, K is 0.2 milli. Then VDS is minus 1,
Minus 1.
VDS is minus 1,
So it will be 1.
VT is
Minus
2.
0. Minus 2.
Okay, so what is VGS now? So 1 milliampere is equal to 0.2 milliampere times 2 times VGS minus VT becomes plus 2. VDS is minus 1. minus of minus 1 whole square. That becomes 0.2. 0.2 and 5 milliampere, you will cancel and take it to the other side.
Volt.
This will become 5. Okay. 2 times VGS plus 2 minus, I will bring it off here. And there is minus times 1. 1 square is 1. So if you
VGS
open
is
this,
minus 5 volt.
minus 2 VGS minus 4 minus 1. Did I do it correctly?
Yes, sir.
VGS is minus 5 volt.
Minus 5 volts.
So VGS is equal to
Minus 5 volt.
minus 5 volt. If VGS is minus 5, right? What is VG?
VG.
VGS is equal to VG minus VS. How much is that?
VS is 5 volt. So when we do VG
VS is
minus
5.
VS is equal to minus 5, we get VG equal to 0.
Correct. VG equal to 0. That is the
Gate
correct
is
answer.
connected to ground.
Gate is connected to ground. Okay. Now in this condition, your assumptions will be correct. Now let us look at what are the assumptions are. Again, VG, VGS, VT. How much is VGS? 0.
Minus.
Sorry,
Minus.
VGS is minus 5.
Minus
Correct. VG is 0. So VGS is minus 5. VT is minus 2. Minus 2. So
VGS is minus 1.
VGS is less than VT here. Got it? VGS is less than VT. Right?
VGS is less than VT and
That means it is device is on.
on. Minus 5.
So our assumption in the previous thing was correct. Next, what is VDS?
VDS is minus 1 and
VDS minus
VDS is greater than VGS minus VT.
So VDS is minus 1. How much is VGS minus VT?
minus 3,
3.
sir.
Minus 3. That means VDS is greater.
Greater.
So what is the next assumption? It is triode region.
Linear.
Okay. So this assumption also second time was correct. Therefore, this is the correct assumption. Okay. With this correct assumption, the final answer is the gate voltage is 0. Understood? So your assumption DC analysis can be iterative. It need not be first time right. And you should be extremely careful about the equalities and inequalities. This is what it is important. Extremely important in circuit design. Okay. Now let us do one more just to see how confident you people are. Okay. Now thank you, Chandana and Lasya Priya. Next we will call on Dhanashri. Okay, the other lady dropped off the moment I called her name. Okay. Farah and Dhanashri, can you please turn on the videos? Let us discuss the next problem. This is the next problem. Problem is you need to find R. Okay, let's find R. So what are information is known to you? It is PMOS device. First one. Second, the relationship between VGS and VT is known. How much is it? VT is -2, VGS is -4. So VGS is less than VT. What does that mean? Device is off or on?
On, sir.
Device is on. Good. That means what are the leftover options for you? It can either be in linear or it can be in saturation. It is not definitely cut off. Okay. So next, let us find what is information available. What information is available? To help you, let me mark. So this is your gate. This is source. This is drain. So first one. What is VD? How much is VD? What is VD?
1 into ID, sir.
1K into ID. Okay.
1K into ID.
1K into ID. Very good. Now, how much is VG? Okay. Let me define a value called the current through this path is I call it IG itself. Okay. So what is the current through this path? How much is IG? IG is equal to voltage at this end to the voltage at the other end. So 15 minus 0 divided by sum of all the resistors in that path, 1K plus 1K plus R. So 2K plus R. Right? So this is the IG. And what is this voltage then? What is Vs? If you don't get this point, there is no way you can solve this problem. So Vs will be the current through this segment multiplied by the resistance. So Ig times 2K. Ig times 2K is Vs. Now what is Vg? Voltage divider ratio, right? R1 divided by R1 plus R2 times Vs. That is 1K divided by 2K times Vs. That is equal to 1 by 2 Vs, half of Vs. Right? So these are the three important ones. ID is how much? How much is ID? Easier way to find out ID is VD divided by R3. VD divided by 1K is ID. Right? Now all this is fine, but still the aim is to find this resistance value R. So for that you need to find all of these. Everything is there. So Vs is dependent on Ig, Vg is dependent on Ig. Vd is there, Id is there. They are dependent on nothing else. So how do you find out the current? VGS value is given. VT value is given. So done, right? People are not speaking up here. Mind is not working. ID is equal to K times VGS minus VT the whole square. Assumption, saturation. What is ID?
3 milliamperes.
3 milliamperes. How much is VGS? VGS is minus 4. Minus of VT 2 times whole square. This is 3 by 4. Minus 4. Minus of minus 4. This will be minus 2. Minus 2 times 4 is 4. So ID 3 milliampere. Right? We now have, in our design space, always remember VGS, VT, VDS, ID, GM. ID is found. What is GM? 2ID by
2ID by VGS minus VT.
VGS minus VT. What is that? 2 times 3 milliampere. What is VGS minus VT? Minus 2.
Minus 3 milliamp per voltage.
Minus 3 milliampere per voltage is GM. Very good. So we have finished these two. We know. We know VGS also, we know VT also. What is pending is VDS. So how do you find out VDS? One important relation you should find out. You see here, VG is half VS. Half VS. So you know what is VGS? VGS is equal to VG minus VS. How much is VGS? Minus 4. How much is VG? Half of VS. Minus VS. So this will be minus 3 by 2 VS. So how much is VS then? Minus gets cancelled, so 8 by 3.
2.66 volts.
2.66 volt. Okay, so now you know VS value, you know 2.66 volt. Correct? Yes or no? Now at this point, you have to apply KCL. So when you apply KCL, what happens? Let me write in this corner here. KCL at node 1. What is node 1 at KCL at node 1? Current, red color current, red I going in splits up into IG current plus ID current. So that is why you needed IG value. Right? Or right now you know that what is the resistance drop across this resistor? 15 volt is there, other side is 2.66 is there. So you know this is a drop here. How much is the drop?
$12.34.
How much?
$12.34.
12.34. So
Papa.
voltage across R is 15 minus 2.66. That will be 12.34 volt. Now to find out R, we need to know VR divided by IR. So what is this I? You will get R. How do you go about getting this? Okay, just to help you, we will write the value of ID. ID is 3 milliampere. Okay. This is another way of applying. You don't need current value for that, right? You need the voltage division. Let me rewrite this curve here. R1 equal to 1K, R2 equal to 1K. This is R value. This is 15 volt. This is Vs. This is Vg. Do we know what is Vs and Vg value? Yes, we know. Vs is 2.66. Vg is half of Vs, that is 1.33 volt. Now what is R? You know how to solve this, right? Okay, people are solving. Let them solve. Give me the answer. What is the answer? Can use Vs is equal to total resistance drop there. How much is it? 2K. I'm sorry, not 1K. 2K into 15 times 2.66. So this will be 30K divided by 2.66. Let us simplify. 2.66 is 8 by 3. 8 by 3. So this is 90K minus 16K by 8. 74 by 8K. 9.25 kilo ohm. It took you so long to just solve this. People need to brush up a lot of things right now. First thing you need to brush up before we start this network analysis. Right? Second, RC circuits. Okay. For Tuesday's class, please review this and come. Network analysis, RC circuits, and algebra. Please revise this before our next class. Okay. So before I start the next session, if you want to take a 5-minute break, please take a 5-minute break and come back. We will resume in some time. Now let's continue the next topic, which is going to be how do you make MOSFET as a switch or amplifier. Now, let us do it with an example so that people understand better. We will start with this example as a simple circuit where a resistance is connected to its drain, and this is the output. So here we have the input, here we have the output. This is our drain is equal to 1 kilo ohm. Total supply voltage is given as 5 volt, grounded. K is equal to 0.75 milliampere per volt square. Now, this circuit is actually a fundamental behavior. Now, we need to determine what is the transfer function. What is transfer function? Transfer function is called defined written as leaks. The output is a function of the input. In this case, the output function is a voltage. The input also is a voltage. So that is why you are going to transfer the input to the output. So it is called only a transfer function. In case if the output voltage was a function of current, then that would be trans impedance function, right? Because now you will find the impedance output by the input. So it is going to be a transfer and an impedance transfer also. So it is transfer. My daughter made for me. Okay, so how do you behave? How you take this transfer function below? So whatever is the input that you apply, you will get an output. What is the best way to find out that is? Apply a voltage source at the input. Keep an oscilloscope or a measurement of the output. Start sweeping it from 0 to the maximum input voltage V in max, and measure the output for each of the input coming out. So that is be a simple transfer function. So how do you determine? Let the VT of this device be about 1 volt. So now what will you get? This is VGS. This is VDS. Current flowing through this device is ID. So you've got all the 4 major design space variables present here. What you have to do, you just have to find them. What is that? How much is VGS? VGS is V input I minus 0. What is VDS? V output O minus 0. Okay, so we found out this. For the next step, simple step is apply KVL. KVL at drain source loop. That is given as 5 minus 1K times ID minus V out, which is equal to VDS, that is equal to 0. So what did we get? V out is equal to 5 minus 1K times ID. Equation 1. Now, do we know what is the value of VGS? We don't know. VT is 1. So what are the conditions we can have for an NMOS device? Assume it is in cutoff. What does cutoff mean? VGS is less than VT for NMOS device. So what happens in this condition? So in cutoff, VGS, VI is less than VT. That is from 0 volt to VT, that is 1 volt. There is output is present. What is the output? It is cut off. So you'll have no current. So VI less than VT, ID equal to 0. Since ID is equal to 0, V naught is equal to 5 minus 0 is 5 volt. Then we can conclude V naught is equal to 5 volt when condition, when VI is less than 1 volt. Okay, here VT is 1 volt. Next region, assume it is in saturation. That means VGS is greater than VT. Then what will happen? First, the ID current. ID is equal to K times VGS minus VT the whole square. That becomes ID is equal to K times VI minus 1 the whole square. What will be the output voltage? 5 minus 1K times ID. That will be equal to 5 minus 1000 times ID, and ID is given by K times V minus 1 the whole square. Right? Now what is K? K value is 0.75 milli. So 1000 into 0.75 milli is going to be 75 or 0.75. 5 minus 0.75 times VI minus 1 whole square. This is another equation. Now, but for condition of saturation, we know that VDS minus VT, what is the other equality? VDS is greater than VGS minus VT. In this case, VDS is V naught, VGS is VI minus 1. So this is the other condition. What does this condition mean here? What does this condition mean? Okay, let us solve this equation. Put this variable here. So V naught is equal to 5 minus 0.75 times Vi minus 1 the whole square. And what is that? Vi minus 1 the whole square is greater than Vi minus 1. Now, if you solve this, what do you get? Now, this is a quadratic equation in Vi. So, the quadratic equation Vi comes Vi minus 1.0 is less than 2.0. In that case, the consistent solution is Vi less than 3.0. That means the MOSFET is in saturation when the Vi is less than 3. But there is one more factor here. There is 1 also. So you will get the equation as follows. So the output voltage is given as 5 minus 0.75 Vi minus 1 whole square. 5 minus 0.75 times Vi minus 1 the whole square. This is the voltage. What is the condition when your Vi lies is less than 3.0 and greater than 1.0? So this is the second condition. So what is the condition that is left off? The condition that is left off is now linear region. What does linear region mean? If you enforce it is in the linear region, what happens? So it is in the, instead of linear, we will call it the triode region. The current will be half mu n Cox, or rather it will be K. K times 2 VGS minus VT the whole square VDS minus VDS square. Sorry, not whole square, VDS into VDS whole square. Now, what is the value you will know? V naught is equal to, sorry, V naught is equal to 5 minus ID times RD. RD is 1K. We will bring that here. ID is equal to so for ID, let us do VD itself. VD is equal to 5 minus K times, and all of these put together will be 0.75 K times 2 times Vi minus 1 the whole square into VDS. VDS is 0 for V naught minus V naught the whole square. And this VD is essentially your V naught. So if you rearrange the equation, rearranging is, here you have V naught and Vi and V naught whole square. V naught whole square multiplied by 0.75, 0.75 V naught whole square. It will go to the other side. So 0.75 V naught whole square. Next you have only one V naught term and you have another V naught term. So minus 2 V naught plus V naught you will get here. So you will get minus 1.5 Vi, 0.75 into 2, 1.5 Vi times V naught. Then you got 0.5 times V naught plus 5.0 equal to 0. Now, if you solve the quadratic equation, solving the quadratic equation, okay, This is A, this is B, and this is C. Quadratic equation defined as the solution V naught will be given as plus or minus, no, it is B plus or minus B square minus AC by 2A. If you replace that equation, what do you get here? B is minus 1.5 Vi minus 0.5 plus or minus B square. 1.5 Vi minus 0.5 the whole square minus A into C. A is 0.75, C is 5. So that is 0.5 into 3 by 4. So that will be how much? 15. Correct? Now this
Sir.
whole value under root.
Sir, B square minus 4AC by 2.
4AC by, that's what I said. So 4AC, that's what I thought I made a mistake. So 4AC is 10. 4 into A is 3 by 4 times 5. Be 50. Yeah. Divided by 2A. Is 0.75 into 2. So you will get 1.5. So if you solve this equation, what will happen? You will realize that there are two possible solutions. Now, for this possible solution, you have one equation, meaning pinch off should not have happened, meaning in that case, VGS minus VT should be greater than your VDS. This is before pinch off. So now what will that become? Your VDS is 0, V naught less than VG, or VGS is VI, correct? So VGS minus VT will give you VI minus 1. So this is the condition that we'll have. Now, what condition can satisfy this one? This plus factor will be 0. So you need to have a lower value. So this one is satisfied by V naught is equal to apology, this was plus. Okay, 1.5 Vi minus 0.5 minus square root of 1.5 Vi minus 0.5, right, by 2. Sorry, square minus 15 divided by 1.5. Apologies for my handwriting. Okay, so the solution with the minus sign is taken. What happens next? So you get a very detailed equation. Now we need to find out where this fits here. Two conditions are defined, right? When Vi is less than 1 and Vi is between 1 and 3. So most probably these are defined for greater than 3 up to the maximum value of 5. Right? Now what is that region called? That possible region is called when your Vi is greater than 3 volt. See, we have reached Vi is less than 1, Vi is between 1 and 3. Next one is Vi is greater than 3. So that is the only region that is left. So we can conclude with the following equation that this condition is satisfied when Vi is greater than 0. So now let us write what is the transfer function. So the transfer function is given as follows. To save some time, I will copy this. So V0 is equal to 5 between a value, 5 minus 0.75 times the input value between this value, and it is this value when it is greater than let me rewrite it better just to make it look. So this will be the next equation when it says it is 1.5 Vi minus 0.5 minus 1.5 Vi minus 0.5 the whole square minus 15 under the square root whole divided by 1.5 when I is Vi is greater than 3 volts. So now we have defined all the conditions for the operation. So this is called the total transfer function, meaning, for example, if you draw a graph like this, this is your Vi. Now there are two references. One is 0, 1.0, 3, and beyond 3 volt. So what does the graph will look like? What will the graph look like? It is 5 till 1. So let this be 5. There will be 5 till 1. From then on, it is a 5 minus a quadratic number. So quadratic number will be like a parabola. It will fall like this. This is the parabola equation. Then comes your triode equation where it is falling fully down. Okay, so these are the three ranges now. NMOS in cutoff. This is NMOS in saturation. Finally, you get the NMOS in triode region. Now, we need to know that this circuit. Now, what is this circuit? Let us refresh back. Now, this is a circuit where you have an input Vi, output V0, power supply given, and an RD circuit. Now, this circuit in this configuration can behave both as a switch and amplifier. Where does it behave in a switch? Switch when it is operating in cutoff and triode. Amplifier when it is in saturation. So this circuit will behave as a switch and as an amplifier depending upon on what region of operation you keep the device in. Right? So this is an extremely useful fundamental. Always remember, right? Now, what happens when you input voltage, you put it at 1 and 0? We will see that in detail. Let us do a small table here. This is your input, this is your output, and this is the mode. Now, if your input is 0, output is 5 volt. If your output is 5 volt or greater than 3, sorry, if your input is greater than 3 and output, your output is 0 or nearly 0. So this is your cutoff. This is your triode. So this is a switch action. Correct? So this is how this particular circuit or NMOS device can act like a switch. So another thing is, coincidentally, you will now associate this switch with all digital circuits. Okay, this is all your digital circuits. And the small voltage that you saw here, which can lead into current, is part of the leakage behavior. So some amount of leakage will come here. It is not going to fully 0. So you have to play with that. So that is your digital circuits. So what is the benefit of digital circuits? All your digital gates, AND gate, OR gate, all your logic gates, etc. Now coming to another important part that you will see. What is the operation here? Now we are looking at an extremely important behavior. Your amplifier is going to be significantly better. How is that? Now let us look at let us go back to the math again. What is the math? Saturation mode, find this equation, right? V out is equal to 5 minus 0.75 times Vi minus 1 the whole square. If you take the derivative, what will happen? What is the derivative? Derivative is dV naught by di, the Vi, and we take the modulus of it. So what is the derivative of this? dV naught by dVi equal to dV of constant is 0, 0.75 stays the same. This becomes 2 times Vi minus 1, which is equal to minus 0.75 times 2 is 1.5. Minus 1.5 Vi minus 1. So that is written as minus 1.5 Vi plus 1.5. So what will happen? Since every change is happening, you get to observe. What is you observe? That the derivative of this circuit this was your V naught characteristic. Now what you will observe is your dV by d naught. If Vi is 0, right, how much is the value? Plus 1.5. So it starts somewhere here. Okay. Did you notice what is happening? When Vi is 0, it is plus 1.5. Till when? If Vi is 1, then dVi d0 by is 0. So if you take only the modulus of this, you will get a factor that is going like this. So this will be dV0 by dVi. Important is modulus. Here what happens is it will go up and down like this. If you take the modulus, it has now moved straight back up. So this is, you will know that the gain in these two regions, right? dV0 by dN, the gain is lower. Observing? So dV0 by dVi is approximately 0, not greater than. Is approximately 0 in cutoff and triode regions. That is these two. And the gain is high in the saturation region. dV0 by dVi is greater than 1 in saturation region. So how is this important? This importance means this you have a higher gain. And when there is gain, there is amplification. So you can use this circuit as an amplifier in the saturation region. So small change in input voltage Vi will give a large change in output voltage V0. Understood? So this is what it is in that case. So every action of an amplifier will have two aspects. So when you are doing a DC analysis of anything, you will have two factors. One, you will have a DC factor plus small signal factor. One performance when it is a very small signal, one performance with a DC signal. And we typically call it as AC. So you can represent any circuit, keep a note here, small v, capital I, okay, as an input. So this is a time varying factor, is given as DC factor written in capital V I, with an AC factor which is time varying, right? So this will be the typical input that you will have. Likewise, your output. Your output also will have small v, capital O in bracket T. You will have a capital V, small o. This is your DC component followed by your AC component. Small v, small o. So this will be your output. Now, in this condition, when we do DC analysis, we will focus on these terms. And when we do AC analysis, we will focus on the smaller terms. So AC analysis is the small vi and small v0. DC analysis is the capital Vi and capital V0. Right? So now we will only consider what is DC and understand what is the DC point or the DC operating point. That should be the maximum slope. So where do you find that? So this is your Vi, this is your V0. The point where you have maximum gain, this region is what you will operate in your DC. So this will be called your DC operating point. With max slope. What is the slope given as? dV naught by dVi. So DC operating point is defined at the area where there is a maximum slope. Okay, so wherever you give the minimum in, maximum in when you get, that is the definition where you define the transfer function. So how do you define that? If you see, this value is now between 1.0 and 3.0, right? Less than 1.0 is your cutoff, 3 points greater than 3.0 is your, what is it? It is your triode region. Now find out what is the DC operating point value. If you draw a line from this graph to here, this will be a DC operating point. So what is this Vi that you give here? What is the V out you approach? Those will be your DC values. So Vi and V naught correspondingly are given here. Now at this point of time, from this here, if you add a small Vi up or down, correspondingly the V out value will go up or down. So this small value that you add is this AC analysis or your small change. This will give you small signal gain. Right? Small signal gain is V out of naught divided by V in. Because now at this DC point, you make a small change, you get an output swing. So you always talk about small signal gain. Typical example, if the input changes by 1 millivolt, if the output might change by 5 millivolt. So what will happen there? Is that a small change? Yes, there is a gain is equal to 5 in that case. So expression will change at that slope. So how do you proceed further? To proceed further is, how do you identify whether this is a value? You come here in this equation, dV naught by dVi magnitude equal to minus 1.5, take it outside common, Vi minus 1. So for this equation, if you apply, Vi is very small, 1 millivolt, that you multiply and get the factor output. So the expression that will change here is, minimum is for your Vi is defined for 1.0 to 3 millivolt only, or sorry, 3 volt only. Now what will be the magnitude of the maximum slope? Maximum slope is how much? It will be minus 3 millivolt per millivolt. Correct? How do you know? When is the minimum slope? So what is your output? What is your output? Or you find out what is the maximum slope you get? dV naught by dVi. What is the maximum? Replace here. If Vi equal to 0, it is minus 2.5. If you make this 0, it is minus 1.5. Right? dV naught by E, Vi, if you make it 0, it is minus 1.5. Minus 1 times 1.5 will be plus 1.5. So at 0, it is 1.5. Now Vi is equal to 1. So this becomes 0. So dV naught becomes 0. Then if Vi equal to 2, this will be 1 minus 1.5, 0 minus 1.5. Then if Vi equal to 3, this will be 2. 2 into 3, it is -3. So this is at 0 volt, sorry, VA equal to 0, VA equal to 1, VA equal to 2, VA equal to 3. Now since we are doing magnitude, this will become 0, 1.5 and 3. So the maximum slope that you will see magnitude wise is 3 millivolt per volt. If you want the direction, you get -3 millivolt per volt. So that is how you identify. You could either say it -3 volt per volt or -3 millivolt per volt is also the same. Millivolt per volt makes more sense because this is the region of interest. So where it is millivolts only. So that is how you will do the slope. So now you understand that when you have a very small voltage, you will get a very large output voltage gain. Any questions? Everybody is extremely silent today. Why? What happened? Too long a class, huh? Probably. I think these participants are down to half. Okay, let's take our customary photograph before we break for the day. Please turn on your videos. Okay. I just want to see the faces. Everybody is drained out. Too much of taking. Next class, we will try and do some lab work. Okay, we'll do some simulations. I need your help in talking to Premateja, to get the lab setup done. Or has anyone tried out LT Spice? If you try out LT Spice, that will also be good. Okay. Venkata Satyasai, your video is not on.